So today's class, we're going to basically model a simple pendulum, like a stick, and then I'll show you how to control the pendulum to do position, force, and torque control. Okay, so as usual, go to tiny.cc MuJoCo, download the template.zip file, put it in the My Project folder you created sometime back, rename that to control_pendulum, and then rename the hello.xml to pendulum.xml. And then you make these 3 changes and then run the control pendulum. So I'm going to do the steps and you can do it with me. Template folder. You can call this anything you want. I'm just going to call it control pendulum. Okay. And then open that up. And we're going to make 3 changes. So first of all, let's open the main.c. Okay, that's the main.c. We'll change this template to whatever you call the folder, control_pendulum. And then instead of having the file as hello.xml, we'll just rename that file. So let's go to hello.xml, rename this to pendulum.xml. Once you do that, you can go here and rename this to pendulum.xml. That's the first change in the main file. It was this. Open the make file. Okay, now uncomment the comment based on your operating system. So for Mac, I keep these 3 active. For Linux, you want to uncomment these, or Windows, these 3. Once you do that, rename this to the folder. So in this case, it's control_pendulum. That's the only change you need to do. Okay, so we can now close this. And then the final change is open the file appropriate to your operating system in text editor. And then we'll change this name from template to underscore. Okay, all set. Now, having done those 3 changes, you want to open the terminal or the x64 shell for Windows. Navigate to your MuJoCo file. So for me, it is in Documents, MuJoCo, My Project. And in this case, I need to go to the control pendulum folder. So cd control pendulum. Now, depending on the distribution, you want to either do run Unix or run Win. Okay, so if everything worked fine, then you should see that block from hello.xml dropping in as shown. Basically, create a free swinging pendulum. And then we will add actuators. And then we'll go back and forth. Then we'll write some code to do torque control, position control, velocity control. And then I'll go back to adding sensors. Because in real systems, you have sensors like a gyro or IMU. And then we'll do a position velocity servo based on, the torque control using that sensor. Okay, so let's get started with pendulum.xml. Okay, so that's so open the pendulum.xml. It is basically the file for a block falling down. Okay, and then at this point, if you might be better off, using the simulate to create this. So what we'll do is we'll modify the XML file and then drop it in the simulate just like we did in the first class, and then we see how modifications in. So I'm just going to navigate back to that bin folder. So if you do pwd, the path to the bin folder is basically after MuJoCo 200 macOS. I need to dial down 2 folders back. So cd dot dot, and then cd dot dot, and then cd bin. And then I can type simulate. So this opens up. And then I can just drop the pendulum.xml. So here I'm going to take the pendulum.xml and just drop it here. Okay, so that's not surprising. Okay, now we are all set to modify this file and then see how those changes reflect in the GUI. Okay, I just need a small window for this. Okay, and reload. Okay. Perhaps a little bigger. Okay, the first thing is I don't really like a box to be my pendulum, so I will change that to a cylinder. Okay, and so again, it's good to have the reference handy. So if you go to MuJoCo documentation, hopefully you've bookmarked this. So the XML reference. If you want to see how to change those properties, you scroll to body. Within that, there's geometry. And then these are the different geometries which you can use. Okay, so we used box here. We can use cylinder. You can read the documentation. The cylinder requires 2 parameters, the height of the cylinder and the radius of the cylinder. So let's just use that. So first change this to cylinder, and then it needs 2 parameters, and I forget which is which, but we can just try point. Let's guess that the first one is radius. So 0.5, and then the height, let's say 0.5. Then we just do reload. Okay, that looks about right. Something which I want to check is 0.5 the length of the diameter, or it's half the length of the cylinder. So if you go here and check for cylinder, radius and half height. Okay, so this is the half height, which means that when I say 0.5, the actual length of this is 1 meter. Okay. Okay, now we need to specify a mass to this. And if you want inertia too, if you go to geom, then you'll see that inertial is one of them. In this case, you can actually specify the mass to the geometry just by typing in mass equals 1. Now, is that right? Let's check the documentation. Geometry. Material, friction, mass. Okay, yeah, so there is a mass option. So if you're putting that, will basically make this cylinder of a mass of 1 kg. Okay, so far so good. And then there's nothing interesting in the dynamics. I'm not going to reload this. Okay, now what we want to do is we want to specify a pin joint so that this can swing like a pendulum. Okay, so this is something which we can do with the joint type. Right now, the joint is set to free, which means that it can move in the XYZ direction, rotate about the XYZ direction. We want to constrain that to a pin joint. And so we again look at the documentation. So I'm looking for joint. It's here. So joint, these are the types of joints: free, boss, slide, and hinge. I want a hinge joint. So I'll change the type to hinge joint. The other thing you want to do is when you choose a hinge joint is to choose an axis, which I'll do shortly. Fitness changes to hinge. And then see what happens. Okay, nothing happens. Okay, that's because probably it's vertical, and so that's why nothing happens. Why don't we actually rotate the object by, I don't know, some angles that, you know, it will probably start swinging like a pendulum. So what I'm going to do is next, I'm going to change the orientation of the geometry, and I can just do that by setting up the Euler angle of the body. So if you remember, we did this previously. Euler equals, so it's 3 values, one for rotation about x, second rotation about y, third rotation about z. It's really hard to see how we want to do it. Let me just show the axis here, it might help. So rendering, frame, world frame. It seems a little bit cluttered. Okay, anyway, so this is the x-axis and this is the y-axis and this is inclined to the z-axis. So what we want to do is either we want to have a pin joint along the x-axis or the y-axis. Both of those will do the same thing. Now, what we can do is we don't quite know where the joint is, but we can just change the angle. And let's assume that we're going to try to rotate this about the y-axis. Okay, so it's going to be moving in the YZ plane because the axis, sorry, XZ plane because the x's are along the y-axis. So let me change the Euler angle corresponding to the y because that's the plane along which I'll rotate. Let's say 30, 0, and then okay. So you can see it rotated by 30 degrees. Then what's interesting is that it actually rotated about its center. Okay, that's how geometry is rotated. They rotate about their center. Okay, we need to see the pin joint, which I can't quite see, and it's not even moving. There must be some reason why it's not moving. So let's try to see if we can show the joint. It's hidden. You know what? Let me close this. Okay. Now, what's interesting is that this joint, you can, if the joint was in the y direction, it could have been shown with an arrow in the y direction, but this joint, you cannot see the joint, and that's because it's actually pointing in the z direction. So I want it to be in the y direction. So what I'm going to do is I'm going to go, I have to choose the joint axis, and I can do that through the joint option. It should be something in the way joint is defined. So let's just go back to joint. So we chose the joint, but we need to choose the axis. So here's the axis. So it looks like the default is along the z-axis as we saw. We want to change that to, let's say, the y-axis. So it'll be 0, 1, 0, indicating that the axis is along the y-axis. Okay, so let's put in the joint axis equals 0, 1, 0. And now if we reload it, it should point the axis in the direction of y-axis. Okay, so there it is. I mean, it's along the y-axis, but if you want it in a better way, you could actually change it to minus y, which means it'll point towards you. And that way we don't have to turn the screen. So that's better. Here in this case, it really doesn't matter if you have it along positive y or negative y. So just keep it like that. So the reason why this is not rotating, that is the pendulum is not rotating, is because the axis is sitting right at the center of mass, right? And so it will not rotate. In order for it to rotate, we need to move the axis to the top or to the bottom. In this case, we'll just move it to the top to make our life easy, and then you should see it rotating. Now the question is, how do we change the location of the joint from where it is right now to a point above? So it's clearly something to do with the way the location where the joint is specified. So let's see if we can change the joint. So we specified the axis, we specified the type. Maybe we can move the position of the joint by looking at the options within joint. So let's go back to the documentation. And you can see this axis, but right here there is position. So right now it is 0, 0, 0, which in this case is the center of that cylinder. So let's change that or move that by, let's see. So we know that this length, the length of this cylinder is 1 meter. So we want to move it on top, which means we need to move it by 0.5 meters along the z-axis. And the reason I say z-axis because think of it like a frame which rotates as the object rotates. So it's the z-axis of the cylinder. It's not the z-axis of the world frame. Okay, so let's set that up. So let's set to POS position equals x0, y0, and z is 0.5. Okay, let's reload. Okay, looks better. Okay, so that's the pendulum which is swinging, and I think we are pretty much done with the creating the pendulum. Now, since we are trying to control the pendulum, now we need to go and set up actuator. So we'll set up the actuator next. Okay, so this will help us to control the pendulum. Okay, so for that, what we do is we go back to the documentation and see if there is something called actuator. The actuator is right here. Okay, so we're going to specify an actuator, and that actuator has there are different types of actuators in MuJoCo. The one we're interested in is it's motor. So it's a position. This is basically a position servo. This one I think is this is not a torque actuator. Let's see if there's a torque. This is a velocity servo. Muscle. Actually, I think motor is the torque actuator. Yeah, this is actually the torque actuator. So what we need to do is first we'll create a torque actuator. So for that, we need to use motor within actuator. And so the way this works is just like we have this world body and world body, we need to create a attribute called actuator. Then it has its own block. So we end it. Okay, now within this block, we specify the actuator. So in this case, the actuator is motor for torque actuator. Now we need to specify where exactly this actuator is going to be put. It's going to be put on this hinge joint. And the way you can tell it that it's this hinge joint is that we will put a name to this actuator, to this joint. Let's call that name as pin. Okay, any name is fine. So this actuator is going to be we'll call it for joint equal to pin. That is indicating that it's going to be for this joint. Okay, we are going to call this actuator a torque actuator. So let's call it name equals torque. And now there are other options which you can put in that. So for example, you could put the control range. So if your actuator is between 5 and plus or minus 5 Newton meters, you can add that. If you want to add a gearing to it, you can add it through gearing. So I'll just show an example, but here we're going to put big enough limits, so it's not really going to be saturated. So gear equals 1, but you can put 10 or 50, whatever you want. You can also put the the control limit. So that's the CTRL limited equals. So CTR limited, you can go through the recommendation, but basically is a range. Is that a range? No, it's basically true or false. Why don't we just see where it is? Okay, yeah, it's true or false. So if it's control limited, it means we need to specify a range. So let's make it true, but then we've not given the range. So the range is right there, control range. So by default, it'll have a range of 0, but we won't really change that. So let's take that, paste it, and then change the range to, I don't know, -100. Say -100 to +100. So that's big enough that it will never really be utilized, but you can change that however you want. So we end this. So that is an actuator, which is a torque actuator. Any questions? Okay, now here's the interesting thing. Once you add this actuator, you can actually do reload. Okay, now if you go to control, you should see that torque appears here. This torque is the name of our actuator. Okay, and then you can use the GUI to set whatever torque you want. So for example, if I set, so remember this is just setting a torque without feedback. So if you set it to some 4, it's going to just start swinging and then go unstable. Okay, let's just reset. Okay, so that's that. Now let's add a position servo. So for that, we need to see what are the options. So position, okay, there it is, actuator position. So this basically behaves exactly like the motor, the torque actuator, except that, right, this one you will set a position, and then it will be doing a position control, which is, think of it like a spring. So in this case, it inherits all the options of actuator, which you've seen before. Some of them I've put there, but has this extra number called KP, which is the position feedback gain. So let's add a position actuator. So the way this goes is you need to, again, create a block for position. So position, and then end the block. And within the block, let's give it a name. Name equals Position Servo. Okay, and then we need to specify which joint it acts on. So joint equals pin. And then we need to give that value for the position gain. So KP equals, and I'm going to put, say, 10. What we'll do is we'll create a velocity servo. So MuJoCo doesn't have a PD control by as a actuator. You can create your own actuator, but you can't do it with what is built in. So what you can do here is specify velocity servo. And if you see the documentation for velocity servo, it's basically the same thing as position, except that there is this KV parameter which you need to set, which is a velocity gain. So KV, and I'm going to put some number 1. So it basically does velocity control. So this one does position control. I need to call this velocity. And the second one does velocity control. And so if you want to set up PD control, you basically combine them. And I'll show you how to do that in a bit. Okay, so if everything looked good, then you can actually reload this. And now if you see in control, you open control, you'll see that you have now 3 options. One is for position servo, velocity servo. So now you can actually change the position. So let's change the position to okay, so one of the issue is that you can see that 0 position is right there, and that's because if you remember, I actually set this up so that it was 30 degrees to the vertical. So I probably need to change that. Right. So I'm going to change it to, so this is 30. I'm going to change it to, if you change it to 0 and reload it, you'll see that it's downwards and there's no interesting dynamics. We want to really move it up, right? We want the 0 position to be up. So all we need to do is rotate this pendulum by 180 degrees in the along the y-axis. So we just change this to 180. Now it'll be vertically up. Everything is right. So you can see it's vertically up. And then if you wanted to move, if you want to check the dynamics, then you probably want to tilt it by an angle, and we'll do that using the code. Now you can actually change the set point for the position servo. So for example, if you wanted at 30 degrees, this is to the right. So positive is to the right, counterclockwise. And then that's negative. So here what's happening is I'm just changing the set point, and then the PD control, because there's a P, there's a D, is actually taking care of ensuring that the angle is maintained. Okay, and so you can drop that down. This won't do much. This is actually supplying a reference velocity. Now, if you want to do velocity control, then what you can do is just put this to 0, put this to 100, a big value, and then reload. And then it's just to, what I'll do is I'll change the velocity command. So it's supposed to rotate at 0.3 meters per second. It'll probably hit that wall and then it won't go. Okay, so another problem with this is we have collision zones, and so it's going to hit that floor. So what we can do is we can turn collisions off, and there's an option to do that, but that will still make it this unpleasant thing that will go through the floor, and that won't look good. So instead of doing that, we'll just move the hinge joint up by, I don't know, 1 meter or something like that, and then it will probably not collide with the wall. So what we do here is we'll go here in the body setting. It's right now set to 1, and then let's just change to, I don't know, let's just say 2. Now reload. Okay, and now hopefully if you do velocity control, it will not hit the floor. Okay, so this is doing a velocity control with a set point of 0.34. Okay, and the position control won't do anything, right? Because we set the position gain to 0. Okay, so if you want to play with this, well, you could just set this to 0, and then you can set this to 5. Now it's basically just a P control, and a P control is like a spring. So let's reload this. And now nothing's going on because it's at the vertical point. But if you want to make it behave like a spring, then what I do is I change the set point to something like this. And so now it's going to oscillate about 0.34. Okay, so this is basically how to use the GUI to check all these things. Now let's quit this, simulate. Okay, and then reset this to 10 and 1. Okay, next thing we'll do is we'll work with the main.c. So open main.c, okay, and let's see that we can run this within the shell. So we are right now in the bin folder, so we need to go 1 level up, and then we need to navigate to my project, and then control pendulum. And then we want to run the Unix or run win. So we need to zoom out, turn this. So you can do this change. I showed you how to do this. You need to uncomment this line right here, printf 185, and then it will print out the view and in the shell. And then you can adjust the screen to whatever angle you want it, and then copy that value and paste it over here. So uncomment this, you paste it over here. So I've actually done that. Well, I have actually figured out what's the good configuration for this. So I'm just going to copy paste that, and that way we can just move quickly. Okay, so what I have is these values. Okay, so I'm going to, okay, now it's a good view. Okay, so once we did this, now let's start modifying the main.c. Okay, so the pendulum is upright, and the best way to check for a position control is to perturb it about at 0. So instead of perturbing it by a small value, like say 30 degrees, we'll just go all the way to 90 degrees, and then we'll try to control the pendulum so it springs back to 0 degrees. So what we can do is, in that case, is we can set the position, the initial position, by doing this, which we discussed in the projectile class. So the Q pose is basically gives me the initial position of all the degrees of freedom. So in this case, there's only 1 degree of freedom, which is the pin joint. And so there's nothing to think about, just should be 0 equals some value. Now, 0 degrees is upright. So we could either put 1.57, which is pi divided by 2, or we could put minus 1.57, doesn't really matter. So let's put 1.57. This is just above the while loop on line 167. So if you do this all right, then you should see that the pendulum is in the horizontal position. Okay, so now it sprung back because there is a PD control, right? But it started off in the horizontal position. It's the key. Okay. Okay, now that we have set the initial position, now we turn ourselves towards, you know what, before we do that, let me just change these gains to 0, because I don't like the fact that it's bringing back 0, 0. So in the XML, just change the gains to 0, line 12 and 13. So once you do that, you can run this to check if it's working as expected. Kill that, run it. Yeah, so that looks like a pendulum which is oscillating back and forth. Okay, that's good. There's no control right now. It's oscillating like a simple pendulum. Okay, so now our task is to create a torque controller, a position controller, a velocity controller, and so on. So let's just do that. Okay, so what we do, the way you define a callback on the controller is that you need to basically set up a function, MGCB controller, and as you can see, MGCB, this is a MuJoCo function, okay, to install a controller equals, we can call the controller whatever name we want, and I'll just call it my controller. And you can check for the documentation of this inside. If you go to the API reference, which I bookmarked, MJCB oh, it's my bad, it's MGCB control. Okay, MJCB control. This is an external MJCB control. It's a callback function. It is used to implement a control law. Okay. And so this is how you define it. You call it MGCB equals my controller. We can call it whatever you want. And once we define that, we will now write this function outside this main function. So go anywhere outside the main function and write down this function, my controller. Okay. Now, the way this is done is it always has 2 input arguments. Those 2 arguments correspond to the pointer to the data and pointer to the model. Okay, and that's like the default. So here we'll put mj model m, and then mj data. In fact, since the model really doesn't change here, you can put constant just to, this is like a protection, just ensures that you're not changing parameters of the model within this. Okay, so if you remove the constant, then you are allowed to change it. If you put constant, you're not allowed to change the parameters. The data, however, is something which you keep changing because that keeps track of the histories, right? Okay, so let me put this in the chat. So this is to be on outside. Just copy paste what I put in the chat. Okay, what might be beneficial at this point, and I should just have done it sometime back when I went to the bin. So you don't have to do this, but I'll just do it and send you the file. I'm just going to create a text file corresponding to this model. And that's really helpful because then I can use that to make this, to understand what I'm going to write here. So don't do this with me. I'm just going to quickly go to bin, simulate, and then drop the Pendulum file. And then I'll say print model, and that will, it'll create the model in the bin folder. Okay, so this is the model. I'm going to send it to you, and you can put it in the same folder as you put this project. Okay, I send it via chat. Okay, so this is actually something which I highly recommend that you always produce it because it helps you to understand what you're doing. So as I said, there is 1 degree of freedom, one for position, one for position, one for velocity. And then if you see NU is 3, that is saying that we have 3 actuators here. One is a torque actuator, one is a position servo, and then the velocity servo. Okay, so what we want here is, well, it defines a bunch of things like, the first body is world, second body, we didn't give it a name, the cylinder, right? But if we had given a name, it would have shown up here. Then there's a joint, we call it pin. Then this is the DOF, which is the pin joint. We define, I think, 2 geometries, one for the world plane and one for the cylinder, light, actuator. Okay, so here is the actuator, it's torque actuator. So our first actuator is the torque actuator. That's something to remember. The second actuator, since index starts from 0, it's the first actuator is the position servo, and then the third one is the velocity servo. Okay, so once we know this, we can use this information to actually set the control command. What we need to do here is the control lies in a variable called CTRL, okay? And the number inside this bracket gives the actuator. So in this case, it's the 0th actuator, which is the torque actuator. Okay, and now since we want to do a position control, PD control, and this is basically 0 equals torque actuator. I'm going to specify a gain, let's say -10, and then I want to compute the position. So it's simply Q pose 0. Okay, so that's, we want it's that minus 0. Our set point is 0. If you want something else, you can put that minus kV, velocity gain, times the velocity. So Q vel 0. Okay, that's it. This is what I'm doing here is I'm computing a position, PD control, and then setting it to the first actuator, which is a torque actuator. And then if this all works, I should actually get the pendulum from its initial position, which is at 90 degrees, to all the way to 0 degrees. So I'm going to put this in the chat. Now let's go back and run this. So you can see it's balanced. Okay, so let's kill this. Okay, so that's the torque control. Now, if you comment this and run this again, it'll actually not do anything. Let's do the position control. So again, if, as I said, the first actuator is the position servo, right? And so in this case, when you use the same command, dctrl, set it to 1, you're actually setting up a position. Okay, so in this case, before I do that, let me convince you that it doesn't work without this. So let's say there's nothing, no control, and you run this, it basically falls. Okay. So once you're convinced, now let's set this to 0.5, or let's say set it to 0. Okay. Now the thing is, I believe I have set the KP to 0, so it'll do nothing. So let me just change that to 5. And remember, this is just setting up P control, which is like a spring. So if this works right, it should sort of go back and forth about the 0 position, which is the vertically upward position. So let's just run this. So that looks right. In fact, you can try to set that position to be 0.5. So in case it will not wobble that way, we've seen 0.5. It'll go back and forth about 0.5. I think the gain is not too high enough. Just increase the gain. Where's fighting gravity? Let's change it to 100. And then run it again. Yeah, so that looks about right. Okay, so let's just put this back to 0, which again will be that it won't really work. It will just swing like a free pendulum. So next thing I'll do is set a velocity servo. So 2 is okay, line 169. Here is line 169. I can copy paste that. Done. Let's go back. Okay, so velocity servo. Okay, now to dctrl 2 equals, now this is basically setting the set point for the velocity servo. In this case, the set point needs to be at, let's say 0.2. Okay? And remember that we set the gain to be 0, so we need to change that. So let's change that to, now if we do it too small a value, then it has to basically fight gravity. And so we make it big enough that it doesn't have to fight gravity. So if this works all right and the gain is big enough, then it'll move continuously at a speed of 0.2 meters per second, approximately. Yeah, so the question is, did you put your controller function instead of main? There's only one thing which I did in the main. If you go to main, then I just did this thing. I just defined the callback, the external file, my controller in main. So once you put this in the main, you can then write that function outside. Okay, so set this to 0.2, set the KV to 100, and now let's run this. Okay, that looks like it's spinning at some slow speed, which is maybe it's 0.2 or a little close to 0.2. Okay, so that looks like it works. Okay, so what we have seen so far is torque control, position control, velocity control. You could actually also do something which people do when they want to check controllers. That is, they want to basically introduce noise and then control based on sensors. So we'll do that step 2. So what I'm going to do is I'm going to define a block for sensors. So if you go back to the documentation for XML, and then let's write sensors. So this is in the sensor block. You can actually define a velocity or a angular velocity sensor, which is basically called a gyro. Okay, so we'll set that up. And then we also want to set some sort of a sensor which gives us the position. So what would that be? That would be, let's see. Is there a sensor which would give us position? Huh. I expected to see something which is like an encoder. Can't seem to see it. Oh, interesting. Okay, so what we'll do is we could set up gyro, but we'll do it in a slightly different way. Since there's no encoder sensor, we will what we'll do is as follow. We'll define our own encoder and gyro. We'll not use this quite use this option. What we want is a joint position sensor. This we'll use this. So we'll have a joint pose as a sensor, and then we'll introduce some noise on the position, and then we'll use joint vel as the other sensor, and then we'll add some noise. And so the way this works is you go to pendulum.xml, just like give an actuator block, we need to define a sensor block. As the first step. Now let's define these options. So joint position. So again, joint pause, that's the option. And within that, we want to set it on some joint, right? So we need to specify which joint it is on. So we'll specify it on joint equals pin, okay, which is the same as pin. And then we want to add some noise. Now, when we add noise, we're essentially adding noise to the position data. So if it's 0.5 position, then it will be plus or minus some standard deviation times Gaussian noise. So what we do is we just specify noise equals 0. I'm just going to make some 0.2. Okay, so that's the sensor for position. Now let's do a sensor for velocity, which is here, joint, where is that? Joint vel. Okay, so again, it's on the joint equal to pin with a noise. Let's introduce more noise on the velocity. So let's just say 1. Okay, now the critical step here is to actually tell MuJoCo that we are dealing with sensors which are noisy. So that's actually an option. So if you search for sensor noise, okay, that's a flag we need to set within MuJoCo that there is sensor noise. So what we'll do is we'll go up right near MuJoCo. We'll have option set up. So option ends. Okay, now we need to give within option, there is Okay, with an option, there is flag. It's really hard to see this, but this flag, if you can see, is slightly indented to the right to option, which means it's an option. Flag is an option within the attribute option. Okay, same for other ones. Okay, so option, we have flag, and then sensor noise. So what do we do with this? Well, let's look at this option. Okay, so we need to say enable or disable. So by default, it's disabled. So let's just enable it. Okay, so I need to share this with you. So let me put in the chat. Okay, so please replace the pendulum file with this new file, which has the noise. Okay, send it via chat. Okay, now it turns out that if you now look at that MuJoCo model, which I will quickly look, cd, by the way, let me first check if there is no error in this cd bin. So you don't have to do this, what I'm doing. I'm going to quickly learn simulate. We drop pendulum, everything looks fine. Let's print model, close this, navigate back. I'm going to open the file. It's in the bin folder. Okay, so here's the model file. I'll open that again. And now it has changed because I added that sensor noise. So now if you go down to this file after actuator, you can see that there's sensor 0 and sensor 1. This was not there earlier when I had not defined the sensor. Okay, so sensor 0, I have not given it a name. If I had given it a name, it would have appeared. So I highly recommend giving names to sensors. Just like put a name, Position Servo, you might want to put a name here. The first sensor is actually the first one I defined here. So that will be the position sensor, and second one is the velocity sensor. So I'm going to show you how to use this. So now let's go back to the main file and let's go to PD control. So we did this for the PD control. Now I'm going to just change this slightly. It's going to be based on sensor data. So instead of putting DQ pose, I just put here sensor. What is it called? Let me check this. It's called sensor data. So that's again the position control, which was the first sensor, and then it puts sensor data, and this is going to be the first one. Okay, so I'm doing a PD control now, but it's using noisy data. So as expected, you will see that it will start vibrating. It will not be a deadbeat like we saw earlier. So let's run Unix. Run Unix. Oh, I see. So I think I've set some gain. Yeah, I need to change. So change this gain to back to 0. I forgot to change it earlier. It's in your pendulum.xml. And now let's run this. Okay, you can see that it is not quite at 0. It keeps shaking, and that's because of sensor noise. Okay, so what I've shown you now is how to do position control, velocity control. PD control can be done by combining position velocity. But the thing is, the last thing I want to do really is to tell you how to actually change these gains in code, because it's not sometimes you want to switch between position control and velocity control, and you don't want to go and change the XML file. So the last thing I want to show is you can actually automatically set the position control, velocity control. You can also disable the position control, velocity control, torque control, and so on. So for that, what we need to do is we need to look at a little bit of the documentation. So if you look at actuator, let's look at the position actuator motor. Okay, so the key thing here is this table. Okay, so there is, when you're setting this actuator, you need to, it's basically setting 1 and 1 for the torque control. If you go and look at the same table for position servo, you'll see that it sets it to 1, it sets KP minus KP. So the key idea here is that what we need to do in order to get to turn the controller on and to change the gain is we need to access gain type and change this KP from KP to 0. It will be disabled. And we also need to do the same thing to bias type. What exactly this is doing is in the documentation, which you can read through. So this is a form in which they use, and basically is a very generic form which you can use to set up many kinds of actuator models. And so they use this form. But what I'm going to do is not really delve too much in the theory or how it is a nice form. I'm just going to show you how you can change these numbers on the fly, and we'll see how we can disable them on the fly. So what we need to do here is turns out that you only need to modify this one, gain type, for the torque controller. We set this to 0 and there's no torque control. If we set these values to 0, then there is no position control. And if you set these values to 0, there's no velocity servo. Okay, so that's all we'll do. So if you look at this gain type, well, it's defined as something called gain PRM. Okay. So this is where it sits. That is in the C file, right? It's the API. Now, this is basically NU times MJN gain numbers. So what's MJN gain? If you look at, so there's MJN gain and MJN bias. So if you search for that, these are like 10 numbers. Again, we'll just print this 10 numbers to see what they are, so we'll know how to set them. But they are NU times MJN. So if there is one actuator, there'll be 10 numbers. Okay. In this case, we have 3 actuators. And since there are 10 of these numbers, it'll be 3 times 10, so 30 numbers. Okay. What I'm going to do is I'm going to print these out for, let's say, the position servo. Okay. And then we'll use that information to reset the position servo, and then use the same idea to do it for velocity and torque control. Let's do that. So first of all, let's disable this. Okay, let's enable the position servo. And go here in the code and set this gain to, let's say, 10. Okay, and run this so that we confirm that it works. Okay, it's about 0.5. Okay. Okay, so now what I need to do is I need to access this quantity. Okay, so the way I access this is that it is first of all sitting in model. So I access it through this pointer. So it will be M points to param. And then as I said, this is going to be, there'll be 30 numbers, right? 30 numbers for all actuators. But since this is going to be, since this is going to be the second actuator, which is NU equals 1, so the numbers will start from, let's say, 10, 11, 12, 13, 14, all the way to 90. Okay, so the easy way of getting this, int actuator number, and this is an actuator number equals 1, right? 0 for the first one. The easy way of getting all these numbers, which I will print. Then the other thing is this is a number. Okay, this is like a double printf new line. So the way I access it is I run a for loop. So for, and you don't have to type this. I'm just showing you what this does, and then you can use this. So I equals 10, I plus plus, so printf actuator gain. So this will be actuator. So this is going to be multiples of 10. So I put 10 times actuator number plus I. Okay, and that's it. And then this is just going to print it just to understand what's going on here. So let's run this. Never. Yeah, I have defined it as number. Okay. Oh, print. Printf is the right syntax. Okay, so that's not the simulation is not very interesting. What we're going to see is this. So you can see that it's set to 10, and this is what we saw in the documentation. So if you look at the documentation for position actuator, the first number is KP, and KP is what we set here, which is 10, and that shows up right here, the first number. So if you set that to 0, then it will basically not do anything. Okay, but that's not the only thing you need to change. As I said earlier, you need to also change this number, bias tab. It's sitting in the second one. To convince you that it's true, what we'll do is we'll find that and print all the variables. So let's do bias. This is what we need. So you can just just watch me, because this is just to show what's going on, but we'll write code which will do something more interesting or will help us to switch. So I'm going to make it print the second one. Okay, so now it should print all the bias parameters. So let's run this. Okay, let's kill this. So you see it's 10 minus 10, and that was basically what we saw. It's the second value is minus 10. Okay, so all you need to do is set that value to 0, and that will be no position control. Okay, so in other words, if you want to set this so this, as you saw, was the 0th element or the first element. So I can set it to any value, KP. So let's say double KP equals 100. And then I can set that. And then I need to also set it as, that would be the first value for the bias, equal to minus KP. So as long as I do this, it will basically set the position gain to 100, whatever I specify. Okay, so there are 3 elements. Okay, so what I'm going to do is I'm just going to make it much easier to set the position control by basically making a function. Okay, it's already 1:45, but I need to go about 5 to 10 minutes over time. I'm going to make a function which basically does this for me on the fly, and I don't have to keep changing it. So what I'll do is I'll set. So take this here. Okay, you can just watch me do this, and I'll send you the code. So void set torque control, set position servo, and then we make a function which does what we want it to do, which is set these values. So it will be based on setting up, as you said, as I showed you, it basically need to specify the actuator number, and I need to specify the gain, and I'm done. So what I need to do is I need to pass the model. So const mj model, and then I need to pass the actuator number, and then I need to pass the KP value. Okay, so all I do is I call this, and then it sets the gain I want. So let's take this, put it here, sorry, this whole thing. I already set the actual number, then I need to pass in. Okay, so let's see, this is set to 10, and now I'm setting it to 100, so you'll see that oscillation is much harder. So let me just first change this to 10, and then see what happens. Okay, that you can keep that in your memory at the speed. Now we're going to make it much faster by setting it to 100. So let's make it 100. And then run this. It's much faster, so it's working. Okay, so we did this, and then of course, if you put it 0, then it basically sets it to free falling, right? No, there's no gain. Okay, so we did this with position. Now we can do the same thing with velocity. It's actually pretty simple now that we know what to manipulate. In this case, if you go to velocity, we need to manipulate the first variable. We need to set it to kV. And then instead of setting the second one, like we had for kp, we need to set the third one to minus kV. So all that needs to be done is take this. I set this to 0 now intentionally. Here, so there's no consequence to 0.5 because there's a 0 kp. So this is actuator number 2. We want to set the kV. It's here set to 0. Okay. So we will change this kV. We want to set the velocity, and then I'm going to write a function called velocity, which essentially does the same thing except it works on kV. So copy this. Paste. So this is velocity, and then this will be kV, kV, kV. And remember that this is not the first index. So for the gain type, it's fine, but this for the bias type, it should be the second one. So now I claim that if this works properly, well, I've set the kV to 0, so it will do nothing first. So let's just check that first. Okay, run Unix. Okay, nothing is going on. Let's just change this to the earlier value, 100. So now it's moving at speed of 0.2, and we set it programmatically in the API. Okay. Okay, the last thing which I'll do is for the torque control. So let's set this to 0. Okay. So that won't be active. And then if you look at the documentation for torque control, it's slightly different from this. You need to set essentially this gain type to 0. That's all you need to do. So the torque control, unlike the position control and velocity servo, is an on-off type of actuator. So we need to set it to 1 or 0. So what we'll do is we'll define something similar for the torque actuator. So here actuator number equal to 1, and then we'll call it int. Let's call it a flag equals 1. That means that the actuator is on. And then we'll create a function, set torque control. And then here it's actuator number, and then we need to set the flag. Okay, so let's define this function. A copy of this. Set torque control. Here I'm dealing with just a flag. Flag. And now this is basically, I just don't need to work with this. Right? And I need to basically do this, which is if flag equals 0, which means that once I set it to 0, I want it to be off, which means that I need to set this number here to 0. So it's the first parameter here. I set this to 0. Okay. Else, if for anything else like 5, 10, 15 for flag, I want it to be on. So this here, and then I say 1. Okay, so this will, I think this will do it. So let's go here and then set our position control. So first of all, let's set it to 0 and see if it actually is not working. Oh, it's working. Why is that? Oh yeah, this is should be 0. Yeah, so it's not working now. Let's kill this. Let's go back and set it to 1. Now it will be this PD control. Okay, so it's working. Okay, the last thing I'll show you here is now that we've worked hard and got this to work, we've got a torque control to work, position control to work, velocity servo to work. You can now define a PD control by just using these two. It's very simple. Just take this code, paste it here, take this code, paste it here. So actuator 1 KP is 10. Actuator 2 KV is 1, and then let's say we want to set it to minus 1, minus 0.5, and then we want this to be 0. Okay, so this is a PD control. So if it works fine, it will actually stop at minus 0.5, which is to the right of the vertical position. I've redefined it. Let's see. We call it 2, 2, 2, 2. Okay, so it looks like, yeah, it's to the right. Okay, so that's pretty much it. So here I show you how you can set a torque, position servo, velocity servo, and combine them to do this. Now, the good thing about having worked this out is that next time if you are trying to set a position, velocity, and the servo, you just copy paste this code, and then you don't have to really do them again.